Okay, we are doing our last section of chapter 10, which is arc length and curvature. This section is pretty heavy on the formulas and the terminology, so there's kind of a lot to follow along with. A lot of formulas to work with here and a lot of different forms of the same formula. So we'll give this a shot, though. We're going to start with arc length. And if you remember, you have already learned several different forms of arc length in 2D. We had just in rectangular form. Your arc length was the integral from a to b, square root 1 plus f prime of x, or dy dx squared dx. We had polar, which was the integral from a to b of the square root of r squared plus dr d theta squared d theta. We had parametric, which was L was the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt, which might also be written as integral from a to b of the square root of dx dt squared plus dy dt squared. Okay, and focusing on that parametric because it's the same in 3D. Okay, integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt, or integral from a to b square root dx dt squared plus dy dt squared plus dz dt squared dt. Okay, and r of t, your vector function, is just those f of t, g of t, h of t. Okay, parametrically, but we've talked about this before. Your vector functions are just like parametric equations, and then you get your t is somewhere between a and b. Okay, another way to put that is L is just the integral from a to b of r prime of t squared. Oops, the magnitude. Hold on, not squared. Getting ahead of myself here. Okay, that part is that is the magnitude of r prime. Okay, so magnitude of r prime of t dt. Okay, right, the magnitude is the components squared, added up, and then square root. It's like your distance formula. Okay, so this is an important equation. This is arc length of a vector function. Okay, so we can get an example here. So let's say r of t is 2ti plus 1 minus 3tj plus 5 plus 4tk. And we want to find the arc length along this curve from 0, 1, 5 to 6, negative 8, 17. Okay, little spoiler here, this is not a very difficult problem because this is a linear function. You guys know that. Linear function through the point 0, 1, 5 parallel to 2, negative 3, 4. Okay, but to make it just a nice, easy example, we're going to use it. But you could just really use the distance formula between those 2 points and get the same answer. But we're going to use our formula there. Okay. And the first thing you need to figure out there is that we're integrating for values of t, right? This equation up here, that dt implies that a and b have to be t values. Okay, so first things first, we got to figure out that here t would be, take a look at your 3 equations. It's pretty clear from the first one, t would be 0. And then use your second ones to just check. Yep, that would give me a y value of 1, and that would give me a z value of 5. And then again, this one would be based on the first equation, t equals 3. And double checking the other 2 equations, that works. Okay. Next, we want to find r prime of t, which would be 2, -3, 4. Okay, so our arc length then would be the integral from 0 to 3 of the square root of 2 squared plus -3 squared plus 4 squared dt, which gives us the integral from 0 to 3 of the square root of 29. Oops. dt. Good notation here. Which is the square root of 29t evaluated from 0 to 3. So 3 square root of 29. Okay. Next, let's see, that is 29, right? I have 2 different things written in my notes. 4, 9, 16, yeah, 29. Okay. Some things that might be useful would be to re-parameterize the curve with respect to arc length. Instead of t. Okay, so our original equation up here, that is useful. I can say, t is usually time. After a certain number of seconds, where am I? Okay, but it also might be useful for me to say, well, when I've traveled this distance, where am I? Okay, so maybe I don't want to know where I am after 3 seconds. Maybe I want to know, where am I after I've traveled 100 feet? Okay, where on that curve am I? So you can see why that might be more useful in some cases. So what we have here is we want to come up with this general arc length formula, which we almost have here. It would be the integral from 0 to t of that magnitude of r prime of t dt. So it would be the integral from 0 to t of the square root of 29 dt, which would be square root of 29 times t. Okay, so that is your arc length as a function of time, v squared root of 29t. Okay, which means we can substitute in t would be s over the square root of 29. Okay, so our function is a function of arc length. Oops, there shouldn't be a, arc length is not a vector. Okay, and that would be, let's see, we're going to replace t with s over the square root of 29. So 2 times s over the square root of 29 I plus 1 minus 3 times s over the square root of 29 j plus 5 plus 4 s over the square root of 29. Okay, So now I can plug in an arc length and see where I am on the curve. So a nice example is, well, how about if I've traveled 3 square roots of 29? Okay, we know from that previous example, right, that after I've traveled a distance of 3 square roots of 29, I should be here. Okay, and we'll see that is going to work out. So it'll be 2 times 3 square roots of 29, or the square root of 29, I 1 minus 3 times 3 square root of 29 over 29, j, plus 5 plus 4 times 3 square root of 29 over the square root of 29k, and I do get 6i minus 9j plus 17k. Okay, so two functions, right, that give you different uses. Okay, this one I can plug in arc length and get where I am on the curve. This one up here, I can plug in time or whatever that parameter is and see where I am on the curve. Okay. All right, the next one I'm going to look at is curvature. Curvature is basically how curvy the curve is. Okay, so you can think of, let's see. Oh, first of all, it has to be a smooth curve. Let me back up a second. Smooth curve on an interval means that r prime is continuous and not equal to 0. Okay, there's no sharp turns. It's kind of like no sharp turns or cusps. Okay, it's going to give you a nice smooth curve. So first of all, that needs to be true. Okay, so if you think about our last lesson with that unit tangent vector, if we have a curve that looks like this versus a curve that looks like this, okay, think about your unit tangent vector as you go along this and how quickly the direction is changing, okay, versus this one. Okay, our function for curvature is this kind of little weird k. K is high where the unit tangent vector changes direction quickly. Right? It's not changing magnitude ever because it's a unit tangent vector, which means the magnitude is always 1. It's the direction. So that's going to be, remember where t, your unit tangent vector, is t of little t, which is r prime of t over the magnitude of r prime of t. Okay, so where dt, ds, okay, and s is where you are on the arc length. Okay, so where the unit tangent vector is changing quickly with respect to the distance along the curve you are, the arc length. Okay, that's your curvature. Okay, and again, I'll write that out. So that is curvature. K is, oh, I got my window open so you can hear traffic. Sorry about that. Curvature K is how the direction changes with respect to arc length. Okay. So you can think about how, like, in order for on this guy, for the direction to kind of do almost a full 180, doesn't take very long along the curve, but on this guy, it takes a longer distance. Okay, so how quickly it's changing with respect to arc length. One thing to know, though, is that we often don't want things in terms of arc length. So this is equivalent to, we want it in terms of t. So this would be, the first one I wrote there, dtds, is you would have to have your unit tangent vector in terms of s to find dtds. Okay, it's much easier. Your unit tangent vector is going to be in terms of t. So this is equivalent to t prime of t over r prime of t. There is a proof in your book for it. I won't worry about it too much. Okay, but there's another important formula for you to know. Okay, so let's get an example here. Oh, and I'm going to back up too. The whole concept of curvature, the way that I kind of think about it is, if you've ever ridden in the scrambler, well, the fair ride, the scrambler, and you're the person who's getting squished when you go around the big turns, it's the point on the ride when you would be getting squished the most is where the curvature is the highest. Okay, so it's all of these guys. That's where the curvature is the highest. That's where that person who gets squished on the ride is getting squished the most. Okay, here this is still the highest curvature, but it's not. It would not have as high of a curvature as the same points on the first one. Okay, so think about, again, if this were the track of like an amusement park ride, when you're getting squished the most. Okay, so an example here, we're going to find the curvature of a circle. Okay, so we know that the equation of a circle is x squared plus y squared equals r. I don't want to use r too many times. I'm going to find the curvature of a circle with radius a. Okay. That's your rectangular equation. For a circle, we know that your parametric equations would be x equals a cosine theta, y equals a sine theta. So your vector function for a circle, r of theta. And we could just as easily use t there. Okay, equals a cosine theta, a sine theta. Okay, so we need to figure out a few things here, right? We need r of t, so we can get r prime of t. And then we need to get t prime of t, which is r prime of t over the magnitude of r prime of t. Okay, so r prime of theta will be negative a sine theta, a cosine theta, and the magnitude, sorry, my thetas are not looking very round. The magnitude of r prime of theta, will be a squared sine squared theta plus a squared cosine squared theta square root, and that can be simplified down to just a, right? You can factor out the a squared, and you know, sine squared plus cosine squared, which is 1, and then you have the square root of a squared, which is a. Okay, so our curvature, again, is going to be the magnitude of t prime of t over the magnitude of r prime of t. Okay, we still need to get t prime of t, theta, actually, which again is r prime of theta over the magnitude of r prime of theta. So that's going to be negative a sine theta, a cosine theta, over A, which is going to be negative sine theta cosine theta. Okay, now we need the magnitude of that for our equation, right? So the magnitude of t prime of theta is going to be sine squared theta plus cosine squared theta square root, which is 1. Okay, so now we have everything we need here. Magnitude of t prime is 1. Magnitude of r prime is a. So there is your curvature of a circle. And it is dependent on the radius. When a is big, the curvature goes down. When a is small, the curvature goes up. And you can think about that in terms of your amusement park ride, correct? Or, just anytime. If you're spinning in circles, if you go in a big circle, you're not going to feel it as much. A little circle, you're going to feel it a lot. Okay. So there you go. You just got to get all the little pieces of it. Okay. Starting with just r of theta and ending with the magnitude of t prime of theta. Okay. There's a lot of steps there, but the formula is very straightforward. Just carefully do your work. Okay. We are 20 minutes into the video. So I'm going to stop it so the videos don't get too long, and we'll just continue right into the second video.